Welcome. In this video, we look at section 4.4, Properties of Relations. We've looked at relations and functions, so today we look specifically at relations, and we discover that there is a lot of interesting things that we can talk about when it comes to relations. So let's take a look. Order relations. So here are two examples of order relations. The relation L on the set 1, 2, 3, 4, such that the pair xy being in my relation means x is less than or equal to y. There's kind of an order is being placed. X is less than or equal to y. Another example, the relation R on the power set of the set ABC, such that the pair set x, set y is in my relation. That means that set x is contained in set y. So again, I'm setting up kind of an order between the elements in this set. Let's think about diagrams. The relation L on 1, 2, 3, 4, such that the pair xy in L means that x is less than or equal to y. What would the arrow diagram for that look like? Well, I list out all my elements, 1, 2, 3, 4, and then we can start drawing arrows. 1 is less than or equal to 2, 1 is less than or equal to 3, 1 is less than or equal to 4, so the arrows go there. 2 is less than or equal to 3, 2 is less than or equal to 4, what else? 3 is less than or equal to 4, and I'm missing something, right? All the arrows that point to themselves, because it's less than or equal. It's that or equal part that's important too. So because of that, every number gets an arrow to itself. What about the diagram for the relation R? And recall the relation R on the power set of 1, 2, 3, such that set x and set y is in the relation means x is a subset of y. Well, this would take too long for me to draw out, so I'll just show you right there. There's the arrow diagram. And does that seem right? Check that the arrows make sense to you, and that, yes, it should make sense that every element gets a circle arrow back to itself. The two relations that we've looked at, the two order relations, L and R, they have some common characteristics. This relation, in fact, these two relations, it's reflexive. Reflexive means that x comma x is in my relation. And we can see this through the loops. Every node gets a loop. The relation is antisymmetric. So in other words, what that means is that if xy is in my relation, and if x and y are actually distinct, then yx is not in the relation. How do I see that in the arrow diagram? The arrows go only one direction. I don't ever have a two-sided arrow. If the arrow goes from x to y, then there is no arrow from y to x. And lastly, transitive. If xy is in the relation and yz is in the relation, then xz is in the relation. How about an example of that? Well, the empty set is a subset of the set that contains 2, and the set that contains 2 is a subset of the set 1, 2. And so, yes, it seems natural that the empty set is also a subset of the set 1, 2. Transitive shows itself by lots of triangles in the diagram. Whenever there's an arrow from one node to another, and then an arrow from that node to a third, then there is the existence of an arrow from the first node to the third node. Relations that satisfy all three characteristics are called partial orders. When we have a partial ordering, it turns out that we can simplify the arrow diagram quite a bit, and what results is called a Hasse diagram. Here are some Hasse diagrams for the two relations that we just looked at, L and R. Here's how it works. If one element is less than another, in the sense, then the one that's lesser we draw below the one that's greater. So this is why we proceed from the bottom to top, 1, 2, 3, 4. Also, we eliminate all of the circular loops that lead back from an element to itself, because we just know that everything is reflexive. And the last thing is we eliminate arrows that would have resulted from transitivity. So 1 is less than 2, and 2 is less than 3, so I also know that 1 is less than 3, but we don't have to draw that in there. From the Hasse diagram, we just simply say, oh, if 1 is less than 2 and 2 is less than 3, then of course we know that 1 is less than 3 as well. So take a look at these two, and especially the one on the right. We can see how the transitivity works there. Set 1 is contained in the set 1, 3, and of course 1, 3 is contained in 1, 2, 3. So we don't need to put it explicitly. From the Hasse diagram we know, oh yeah, 1 is contained in the set 1, 2, 3. Also, let me talk a little bit about this word partial. The partial part of this means that we can't necessarily compare every two elements. The 1 and the 3, one is not any greater or less than the other. Neither is contained in the other. I can't really compare those two elements. And so that's why partial appears. Now it turns out this diagram on the left actually is a slightly different creature, and we'll talk a little bit more about it in a minute, but that is an example of a total ordering, where every possible pair of elements can be compared. So we have a total ordering on the left and a partial ordering on the right, but in fact every total ordering is also a partial ordering. How about a little practice? Consider a relation D on the set 1, 2, 3, 6, where AB in my relation D means that A divides B. Draw the arrow diagram for the relation D, verify that this is a partial ordering, and draw the Hasse diagram for D. Okay, take a couple minutes, give it a try, pause the video, and then start up again to check your work. Okay, let's take a look. So first of all, draw the arrow diagram for the relation D. Here we have 1, 2, 3, 6, and every node gets a circle around it. Every element divides itself. 1 divides 1, 2 divides 2, so we got that. 1 divides 2, 1 divides 6, 1 divides 3. There's no arrow going across because 2 and 3 don't divide each other, but then every arrow goes points towards 6 because all of those numbers divide 6. So there it is. There's the arrow diagram for the relation. Is this really a partial ordering? What are the three things we have to check? How about reflexive? Is this relation reflexive? It is because every node has a loop. So every element loops back to itself. There's an arrow to itself. Is it antisymmetric? Yes, it is, because whenever I see an arrow going in one direction, I do not see the opposite arrow pointing in the opposite direction. All right, antisymmetric. Is it transitive? Yes, because when I see things like 1 to 2 and 2 to 6, 1 to 6 is also there, 1 to 3 and 3 to 6, then 1 to 6 is also there. We can just check that. So it is all of those things, so indeed it is a partial ordering. Since it is a partial ordering, then I can draw the Hasse diagram, and it looks like that. There you go. Moving on. Other types of orders. A relation R is irreflexive if XX is not in relation for all X. So this is the extreme opposite of being reflexive. With reflexive, every node had a loop on it. With irreflexive, no nodes at all have any loops. Now, if we have something that's irreflexive and antisymmetric and transitive, then this is called a strict partial ordering. Previously, we had a partial ordering like less than or equal. That was not strict. But if I have a partial ordering where I have a strict inequality, that could be considered a strict partial ordering. Now, if every pair, xy, is in R, we say that R is a total ordering. We saw something like this earlier, and in fact, if you think of all the integers, or all the real numbers, with our usual inequality, then that's an example of a total ordering, because any two real numbers can be compared with a less than symbol. But we also saw, in examples of sets, that not any two sets can be compared with set containment relation. Here's an example. Consider the relation R with the rule xy is in the relation if x is strictly less than y. This is a total ordering on the natural numbers. In fact, we could call this a strict total ordering. And a little more practice. How about this? The relation R on the integers has this rule. AB is in my relation if AB plus B is odd. All right, take a couple minutes and determine if R is reflexive, irreflexive, antisymmetric, or transitive. So yes or no for any of those. All right, take a minute, see what you can do, and then start up again to check your work. Here we go. Let's take a look. Number one, reflexive. Is this relation reflexive? And the answer is no. All you need is one example, and 2 comma 2 is not in there because, let's see, 2 plus 2, that's an even number, so no, definitely not in our relation. Is it irreflexive? And actually it is, yes. Now if I want to test that, how would I see that? I would say, how about A comma A? Is that in my relation? Could it ever be in my relation? And for it to be in my relation, I would need that A squared plus A would be odd. But with a little bit of investigation, you can probably convince yourself pretty easily that this is never true. It's never true that A squared plus A is odd. So I never have an arrow pointing back to itself in this relation. How about antisymmetric? It is antisymmetric. If AB is in my relation, then BA is not. Now, how did I figure that? Here's how I thought about it. Let's take a look at this original requirement. We need that AB plus B is odd. Well, what that really means is that A plus 1 times B is odd. And the only way I can have a product of two integers that's odd is if both of those integers are odd. So in fact, that's the same thing as saying A is even and B is odd. So in fact, you could have looked at this right from the very beginning and sort of translated this relation into a slightly different language. And you can see reflexive, no; irreflexive, yes; antisymmetric, yes. Because if A is even and B is odd, then switching them around will not be in my relation because I need an even number as the first component and the odd number as my second component. Transitive. Transitive is a weird one. In this case, the answer is vacuously true. It's true for a dumb reason, for a trivial reason. So if AB is in my relation, this tells me that A is even and B is odd. If AB is in my relation, then BC can't be in the relation because B is odd. So I never get a chance to actually see transitivity in action. Transitivity, I have an arrow from one point to another, and from that second point to a third. I never have that in this particular relation. So indeed, whenever AB is in my relation and BC is in my relation, whenever that happens, then yes, AC is in my relation also. Of course, that never happens. This is why it's vacuously true. One way of also considering this is that there's no counterexample. A statement is false if there's a counterexample, and a statement is true if there's no counterexample. In this case, there's no counterexample, so the statement of transitivity is true. It's not a great reason, but oh well, there it is. Lastly, before we leave this example, since this relation is irreflexive, antisymmetric, and transitive, we know that this is a strict partial ordering. One more chance to practice. Take a look at this relation. It's not given by any algebraic rule, it's just a set of ordered pairs. Given this set of ordered pairs that defines the relation, what do you think? 1, 2, 3, 4. See if you can answer yes or no for each of these. Again, pause the video, start it up again to check your work when you're ready. All right, the answers. Reflexive? No. Irreflexive? No. How about antisymmetric? Yes, whenever I see a pair like 1, 8, I never see 8, 1. Or if I see 2, 4 in there, I never see 4, 2. So a pair and its reverse are never both in there. How about transitive? Yes, it is transitive. There are a couple instances I think we can check where the transitivity works. For example, 2 goes to 4 and 4 goes to 8. And I look, does 2 go to 8? Oh yeah, so 2 to 8 is also in there. I think there's one other example. Maybe 1 goes to 4. Oh, there it is. 1 goes to 4 and 4 goes to 8. So is 1, 8? There it is. And 1, 8 is in there as well. And with a little bit more checking, I think we see that there's nothing that breaks the rule of transitivity. So yes, yes to transitivity. And this concludes our video for today. In this video, there's a lot of new vocabulary, so be careful, look over it again, make sure you understand what all the different words mean, but also a lot of neat ideas too. Alright, so we'll stop there.